Welcome to AI Paper Slop. Today we're looking at a paper from Michael Y. Liu, Anthony Zahn, and their team at Stanford called QuasiMoTTo, Quasi-Monte Carlo Test Time Scaling.
A really clever approach to sampling.
Totally. And if you scale inference compute, or you run reinforcement learning pipelines, here is the immediate executive summary. Right now, scaling relies on parallel sampling, specifically independent and identically distributed samples, or, i.i.d.
Right, which is standard.
But independent samples are actually incredibly wasteful. Because they're independent, they just clump together in high probability regions of the search space.
Yeah, you're exploring the same dead ends over and over.
Exactly. So QuasiMoTTo fixes this by replacing those i.i.d. samples with correlated Quasi-Monte Carlo, or QMC samples. By reparameterizing autoregressive sampling as inverse CDF sampling, they generate exact samples from the language model entirely in parallel, but with vastly superior coverage.
It forces the samples to spread out.
Right. And the result is wild. They match standard i.i.d. pass at K accuracy with up to 47% fewer samples in inference. And they cut the training steps for RL pipelines, like GRPO, by 50%.
I mean, it tackles a massive inefficiency that, honestly, the ML field has largely just accepted as the cost of doing business.
Because i.d. makes scaling trivial, right?
Exactly. We use i.i.d. sampling because if sample A has no relation to sample B, you can just fan out the workload across, 10,000 GPUs without any communication bottleneck.
Which makes total sense for hardware utilization. But we really need to talk about why that independence is so computationally toxic for actual problem solving.
Right, the hidden tax of test time compute.
So when we talk about test time scaling, the goal is to generate Cully distinct attempts for a prompt. You're just hoping that at least one of them finds the correct reasoning path.
That's the pass-A metric. The probability you get one or more correct answers within that budget of K.
Yeah. And to maximize your pass at K, you desperately want every single sample to try a different approach. It's like, imagine you're blindfolded and you're throwing a handful of darts at a dartboard.
Okay.
You might hit the bullseye, but because every throw is totally independent, you're almost guaranteed to clump half your darts in one random corner, right? You just leave the rest of the board entirely empty.
Yeah, and in a language model, that dartboard has massive gravity wells.
Yeah.
These highly likely sequences of tokens that the model naturally gravitates toward.
So the darts just keep landing in the same spots.
Exactly. If you query a model to solve a hard coding challenge, like 64 times independently, those 64 samples blindly fall into the same 2 or 3 gravity wells. They will write the exact same flawed for loop dozens of times because, well, they're completely unaware that another sample has already explored that specific chain of thought.
So you end up having to artificially inflate your M budget. You're forced to generate 128 or 256 samples just to overcome that clumping. You're just praying that one random stray generation happens to wander into the correct, lower probability path.
And that is exactly why i.i.d. sampling is so wasteful. If you want true coverage of the solution space, you need correlation. You need the samples to actively repel each other.
But historically, correlating samples destroys the very parallelization that makes scaling compute viable.
Right, it serializes everything.
Because if I have to generate sample A, evaluate it, and then explicitly condition sample B to avoid sample A's path.
You're not parallel anymore.
Yeah, exactly. Generating 64 sequential rollouts on a single GPU totally defeats the entire premise of test time compute. So the big mechanical question is, how does QuasiMoTTo manage to correlate these samples so they avoid clumping, but keep the actual token generation embarrassingly parallel?
They do it through reparameterization. So standard autoregressive sampling usually uses techniques like the Gumbel max trick, where you add independent random noise to the logits and then pick the max token. QuasiMoTTo just discards that entirely.
Okay, so what do they use instead?
They use arithmetic coding, which fundamentally maps a single one-dimensional uniform random variable directly to an entire token sequence.
Let's visualize this for the listener because the engineering here is really elegant. Imagine the language model's probability distribution as a massive weighted prefix tree, a triangle.
Right, a massive branching tree of every possible word.
You take the continuous unit interval, so the space from 0 to 1 on a number line, and you partition it based on the probabilities of the very first token. So if the token for def has a 20% probability of starting a Python function, it gets the interval from 0 to 0.2.
And import might get 0.2 to 0.3 and so on.
Exactly. And then you recursively partition those intervals. Inside the 0 to 0.2 bucket for def, you subdivide that specific space based on the probabilities for the second token.
Conditioned on the first token, yeah. So you are constantly zooming into smaller and smaller sub-intervals with every new token you generate.
Which means that every single possible sequence of tokens the model could ever generate corresponds to a highly specific microscopic slice of that 0 to 1 interval.
Yes. And here is the magic part. To pick a sequence, you only need to draw a single random number. Let's call it u, between 0 and 1, before you even start generating.
Right. So if your u is 0.15, you just trace the tree. It falls into the first bucket, so the first token is def, and you just keep checking which sub-bucket it falls into for every single subsequent step.
That single upfront uniform variable dictates the entire path. And that is how you preserve the parallelization.
Because every one of your K-samples only needs its own starting S.
Exactly. They never need to communicate during the actual token generation phase. You do all the correlation work before the GPUs even spin up.
Oh, wow. So you just mathematically arrange a batch of K uniform numbers so they're perfectly spaced out across the 0 to 1 interval, and then you just hand one number to each parallel process.
The generation is completely independent in terms of hardware execution. The GPUs just calculate the inverse CDF mapping to translate their assigned uniform variable into a sequence. No communication needed.
Okay, wait. I have to pause on the math here, because spacing out those starting variables sounds like we are crossing a dangerous line.
How so?
If we deliberately engineer the starting variables to repel each other, we aren't drawing randomly anymore. We are forcing a distribution. So doesn't that mathematically corrupt the language model's actual output distribution? Like, if we warp the probabilities, aren't we just hacking the logits?
It intuitively feels like a contradiction, I know. But the resolution is found in the difference between marginal and joint distributions. The paper points to figure 2 to illustrate this perfectly.
Okay, break that down for us.
Correctness, which means getting a mathematically pure, unbiased sample from the LM's true distribution, only depends on the marginal distribution of the individual sample.
Right, the sample in isolation.
Exactly. If you look at any single, in complete isolation, ignoring the rest of the batch, it just has to have a strictly uniform probability of landing anywhere between 0 and 1.
So as long as a single sample is still unifinc 1 on its own, the inverse CDF mapping guarantees it translates to an exact draw from the model.
Yes. The marginal correctness is perfectly preserved. The joint distribution, how the variables behave relative to one another as a group, that's where we have total mathematical freedom.
Oh, okay. So we can manipulate the group dynamics without ruining the individual math.
Exactly. Think of a simple antithetic pair. You generate a completely random number u. Your second number is explicitly set to 1 minus u.
So they are perfectly negatively correlated. They heavily dictate each other's position.
Right. But if I hide one from you and only show you the other, you literally cannot distinguish it from a pure random draw. It is still uniformly distributed between 0 and 1. QuasiMoTTo leverages that exact principle across ill conventions to maximize coverage without breaking the underlying probabilities.
That opens up a massive design space. I mean, if the joint distribution is entirely ours to engineer, how do we actually space out the U values?
So the authors test 3 specific Quasi-Monte Carlo, or QMC, samplers. They look at lattice, stratified, and token-level Sobel sampling.
Let's run through those. What's the lattice sampler?
The lattice sampler places your K points on a rigidly fixed grid. So if you're generating 4 samples, you place them exactly at 0.25, 0.5, and 0.75.
But to maintain that marginal randomness we just talked about, you have to shift them, right?
Right. You generate a single random shift value between 0 and 1, and you add it to all 4 points, wrapping around the interval if a point goes past 1.
Got it. So it's a rigid constellation of points that slides along the number line together.
Exactly. Now, the stratified sampler loosens that up a little bit. You divide the 0 to 1 interval into K equally sized buckets.
Okay.
But instead of fixing them on a grid, you independently draw one random point from within each bucket.
Which ensures you get like one sample from the bottom quartile, one from the second quartile, and so on. But their exact positions within those strata are completely random.
You got it. And finally, there's token-level Sobel. Instead of working with a single 1D interval for the whole sequence, this method uses a high-dimensional Sobel sequence, where the sequence length n becomes the number of dimensions. It systematically covers an n-dimensional cube, mapping each coordinate to a specific token position.
So looking at those three flavors, the choice really seems to hinge on a trade-off. The authors frame it around mutual information, right?
Yeah, they describe it as a spectrum between freedom and coverage. Lattice has maximum coverage because the points are mathematically forced to be equidistant, but it has zero freedom.
Because if you know where one point is, you know the exact location of the entire batch.
Right. Whereas stratified sampling offers a middle ground.
Yeah.
You know a point is in a specific bucket, but you have no information about where it sits inside that bucket.
And standard i.i.d. sampling has maximum freedom, literally zero mutual information between the samples, but terrible coverage because they just clump together, which ironically introduces a completely separate problem for the researchers. Because by prioritizing coverage and stripping away the independence of the samples, they effectively broke the standard evaluation metrics that the ML community uses.
Yeah, they completely invalidated the core assumptions of the math.
Like, take the pass at K metric we defined earlier. The standard mathematical formula for estimating pass at K from a smaller test set is 1 minus 1 minus P, all to the power of K.
Where P is the pass at one rate.
Right, but that entire formula relies on the assumption of independent binomial trials.
Which you no longer have.
Exactly. The moment you use a lattice sampler, the samples are deeply deterministically correlated. If you plug QMC results into the standard pass at K formula, it outputs total garbage. So they had to invent new estimators from scratch just to prove their own paperworks.
It was brilliant how they did it. For the lattice sampler, they introduced the dyadic bootstrap estimator. It relies on the geometric properties of the lattice itself. If you take a randomly shifted, equally spaced lattice of points, and you look at a stride 2 subsequence.
Meaning you just look at every second point in the grid.
Exactly. That subsequence is fundamentally just a lattice with half the density.
Oh, wow. So if my original batch size is 8, and I pull out points 1, 3, 5, and 7, those 4 points are still perfectly equidistant. They form a valid, randomly shifted 4-point lattice.
Exactly. That structural invariance allows them to take their full generated batches, systematically subsample them using these stride sequences, and calculate unbiased pass at K estimates for smaller values of K, all without violating the assumption of the sampling method.
That is extremely clever. But they also had to navigate a similar mathematical hurdle when they moved to reinforcement learning baselines, right?
Yeah, because in RL, algorithms rely heavily on leave one out, or RLO estimators.
Right, where you evaluate how good a specific reasoning path is by comparing its reward against the average reward of the rest of the generated batch.
It acts as a baseline. But for the gradient update to be unbiased, that baseline average must be statistically independent from the sample you are evaluating.
Which is impossible with Quasi-Monte Carlo, because the samples deliberately repel each other.
Right. It creates a slight baseline bias. Now, the authors note you can technically correct for this using a complex pairwise importance sampling equation that factors in the joint probability of generating any specific pair of sequences.
But that sounds like a lot of heavy computational overhead.
It is. Empirically, though, they found the bias was actually small enough that they could usually just ignore the correction entirely without breaking the training loop.
Well, let's get to the empirical payoff. We've established how to perfectly space out samples without breaking marginal correctness and how to accurately measure the results. Does this engineered coverage actually translate to using less compute at test time?
The benchmarking was done on Quinn 3.5 using 4 really rigorous reasoning domains. You have Countdown, which tests arithmetic search, Maze for spatial planning and backtracking, Sudoku for complex constraint satisfaction, and 1DARC for pattern induction.
And across the board, the results are highly definitive.
Very definitive. The lattice sampler just clears the field. It matches the pass at K accuracy of standard i.i.d. sampling using 25 to 47% fewer samples.
That's huge. You are getting the exact same problem-solving capability while literally turning off a third of your GPUs.
It's massive efficiency.
And I think the most revealing part of the test time results is Theorem 2 in the paper. The authors actually calculate the absolute mathematical upper bound for any sampling strategy that maintains the target marginal distribution.
Right. They define this union-bound ceiling as the minimum of 1 and K multiplied by P, where P is the single-shot pass rate.
So it defines the strict theoretical limit. Unless you train the model and fundamentally change its underlying weights, you cannot extract more capability than that ceiling allows.
You can only optimize how efficiently you search the capability that already exists.
Exactly. And when you look at the performance charts for QuasiMoTTo, the lattice curve practically touches that absolute upper bound. It saturates the ceiling. They haven't just improved test time sampling, they've essentially squeezed every last drop of efficiency out of it.
There is virtually no room left for another training-free sampler to beat this.
It's wild. But test time scaling is only one side of the coin. The most computationally expensive phase of deploying these models right now is reinforcement learning.
Oh, without a doubt.
RL pipelines are burning massive amounts of compute to align models for complex reasoning. So how does QuasiMoTTo plug into something like GRPO?
Well, because it provides exact marginal samples, it's a literal drop-in replacement for RL frameworks. You don't need to rewrite your loss functions or alter the model architecture. You just swap out the sampling mechanism.
But for the ML engineers dealing with RL scaling, we need to dive into why this provides such a massive boost to GRPO. And it comes down to a concept called zero variance groups.
Right. So in group relative policy optimization, or GRPO, the model learns by generating a group of rollouts, say 8 different attempts at a math problem, for a single prompt. It scores all 8, calculates the group average, and then updates its policy by analyzing which specific rollouts performed better or worse than that average. The learning signal relies entirely on the variance in those outcomes.
So if there is no variance, there is no signal.
Exactly.
So if you use standard i.i.d. sampling to generate those 8 rollouts, the clumping effect we talked about earlier just takes over. The model might generate the exact same failed reasoning path 8 times in a row. They all score a 0. The average is 0.
And the advantage function for every single rollout is 0. Or, conversely, they all take the exact same successful path and score a 1, which also yields 0 variance relative to the average.
In either case, the gradient update is just flat. You just performed 8 massive forward passes, evaluated the rewards, ran the backward passes, and the model learned absolutely nothing.
It is purely wasted compute.
But QuasiMoTTo actively prevents this. Because you map uniform variables to the token space and force those variables to repel each other, the 8 rollouts are mathematically prohibited from taking the exact same path.
Right, they're forced into different regions of the sequence space.
So you drastically reduce the frequency of those zero variance groups.
Because the rollouts explore distinct paths, some succeed while others fail, providing a rich, high variance signal. This increases your effective sample size. A much larger percentage of your prompts actually contribute meaningful gradient updates to the model.
And the efficiency gains here are even more pronounced than in inference. When they applied QMC to RL training on the maze and Sudoku environments, the models reached their target pass at 1 threshold in 50% fewer training steps compared to the i.i.d. baseline.
You are literally cutting your RL training compute in half.
That's incredible.
There is a really fascinating nuance in the RL results, though. While the lattice sampler dominated the test time inference benchmarks, the stratified sampler actually outperformed lattice in the reinforcement learning context.
Wait, really? Which seems counterintuitive based on that mutual information spectrum we talked about earlier. Because lattice has perfect coverage. If coverage prevents zero variance groups, lattice should theoretically be the best for RL too. Why does stratified sampling win?
It circles back to the RLO baseline bias. Lattice has perfect coverage, but zero freedom. The samples are rigidly locked together. That extreme structural strictness introduces a slightly larger bias into the leave one out baseline that GRPO uses to calculate advantages.
Oh, I see. In raw inference, bias doesn't matter. You only care if the final answer is right.
Exactly. But in RL, you are actively updating weights based on those gradients. The slight bias from the lattice sampler creates friction in the training dynamics.
So stratified sampling hits the Goldilocks zone. It still forces the samples into separate buckets, giving you vastly better coverage than i.i.d. to prevent those zero variance groups. But the randomized placement within those buckets provides just enough freedom to keep the baseline unbiased and the gradients clean.
It is a perfect demonstration of how different phases of the ML lifecycle require totally different mathematical trade-offs.
Bringing this all together, the value proposition for anyone building or deploying language models is pretty staggering. QuasiMoTTo offers 25 to 50% compute savings across both test time inference and RL training.
And the implementation overhead is essentially zero.
Right. You generate a batch of coordinated uniform variables up front, you pass them to your workers, and you carry a single residual coordinate through your standard arithmetic decoding loop. It is practically free optimization.
It completely rewrites the cost-benefit analysis for scaling parallel compute. But, the mechanics here are proven on symbolic reasoning task environments like Sudoku or maze, which are complex but have very compact, heavily constrained vocabularies.
So where does it go from here? What's the next frontier?
The next step for this research is scaling dependent sampling logic to massive open-ended domains. like generating long mathematical proofs or conducting automated scientific discovery.
Right, where the token space is massive and unbounded.
Exactly. In those unbounded spaces, the prefix tree of token probabilities becomes incredibly noisy. Determining whether two generated scientific hypotheses genuinely overlap or repel each other requires moving beyond just raw tokens.
So we have to start defining semantic equivalence classes.
Exactly, where two entirely different sequences of words actually represent the exact same logical approach.
Oh, wow. So if we can map the mathematical repulsion of Quasi-Monte Carlo onto semantic meaning, forcing a model to explore structurally distinct ideas rather than just different token paths,
It will fundamentally alter the way we use AI to search for novel solutions.
it's a completely new paradigm for mapping the search space of human knowledge. We will leave you, the listener, to explore the implications of that on your own. Keep building, and thanks for joining this deep dive into the source material. We'll see you next time on AI Paper Slop.